Well, hello and welcome YouTube, Mr. Robson back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step on inside and we are looking at the Chapter 7 review out of the textbook Big Ideas Math from Integrated Math 2. It has 5 sections, 7.1 to 7.5. I'll read them off as we go because all the problems are listed in order. This is a problem set. If you would like to find it, go to this description section down below and click on that link where I have the PDF upload or download for you, if you will, and as well as the timestamp for every problem that we do. I'm going to jump straight into it, guys. If you'd like to pause this thing and get that printout ready or get that thing open, grab your binder paper and such, go ahead. This should go pretty smoothly. It's 28 questions. We do a lot more for actual problem sets, and in those problem sets we tend to have a lot bigger like word problems, conceptual things, proofs, construction. I do not believe that'll occur here. This is more of the drill and kill, see how you go. Ready? All right, here we go. We'll start, well actually here, before starting a problem, let's look at what we're going to look at, section 7.1, angles of polygons. So this was before just quadrilaterals, finding interior angle measures or sums, exterior angle measures or sums. I can't remember what else was in this section, but from these problems, that's pretty much all we're going to do. Find the sum of the measures of the interior angles of this figure. You determine what kind of shape it is by the number of sides or angles, which should be the same, by the way, 6. And that's a hexagon. So we have this 180 times n minus 2 formula. I know it says n minus 2 times 180. I write it the other way. So whenever you see me write it, I have this d, degree sum, is 180 times n minus 2. This is for the interior angle measures. Not exterior, but interior. 6 sides, n is the number of sides, so 6 sides there, plug it in, and you get 720 degrees. That means when you add boom, 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 boom angle measures, you get 720, and that's the answer to that one. So let's do a problem for ourselves. Let's see if it's the exact same kind of question. Find the sum of the measures of the interior angles of a regular 30gon. Then find the measure of each interior angle and each exterior angle. So it's interesting how they asked this question, because if they didn't ask the first part, I would have gone about this a completely different way. And I'll show you other things that we can do for the exterior angle measures if needed. Now, a regular 30gon means a 30-sided polygon, all with equal sides and angle measures. The sum is going to be the same regardless of whether it's regular or irregular. N is 30 in this case. So D is 180 times 30 minus 2. And I regret immediately not having a calculator on hand. I have my phone right here. Give me 1 second. So I have to, hold on, equals 180 times 28. So now I have to do that. I'm sure we've seen this number before, even with problems for ourselves. 180 times 28. And I'm getting 5040 degrees. So this is the sum of the interior angles of this 30-sided polygon. Again, whether regular or irregular. However, because it is regular, we can also find the measure of each interior angle. There are 30 sides, keep in mind. I can find each interior angle measure, because they're all the same, by dividing the sum by the number of sides there are, because it's also how many angles there are as well. And once again, I just dropped the calculator for this. Let's do this. 5040 divided by 30. 168 degrees. And then the exterior angle measure bit, you can do one of two ways. One way, an exterior angle measure, if you look at number 4 here, this is an example of exterior angles. I'm not doing number 4 right now, I will in a bit. But exterior angles are not the entire outside of an angle like this. It's just a linear pair form with an interior angle measure right here. And I say linear pair very intentionally. They're supplementary with their interior angle measures. So each exterior angle measure, you can do 180 minus 168, for example, and get 12. That's the measure of each exterior angle measure of this polygon. Remember, it is a regular polygon. Now, that's one way to do this problem, and it's probably the way that I would recommend you doing it, especially because we had to get the sum. I did mention that if they didn't ask us for this first part, though, I could probably do this part a lot faster. And you might wonder how you can get the interior angle measure without the 5040 thing. Well, here's how. You get the exterior angle measures first because their sum is not based on a formula. their sum is always 360. So here's another way that I could have gotten E, and in turn how I could have gotten I. E takes the sum of the exterior angles, 360. It's always 360. Doesn't matter irregular or regular. Doesn't matter if it's 3 sides or 300 sides. In this case, it's 30 sides. You divide by the number of sides or angles there are, given that it's regular, and that's where you get your 12 degrees once more. And then you can get the I. Let me do this in a different color here. And then you can get that I by subtracting 12 from 180 for the same reason that E is 180 minus 168. So I could also in turn be 180 minus 12, which is 168. And like I said, it's the faster way I would go about that problem if those were the only two things that I was asked to do. Now, you could have still gone this method here and here. If you wanted to find the sum, just multiply 168 by 30. It still works. Either method is fine, but because we had to find the sum first, I kind of recommend you go off of that way. Anyway, I spent a lot more time on number 1 than I probably will for some of the other problems, at least for description, and here's how we can do it and things like that. But it's a nice gesture in recalling how this stuff works. All right, find the value of x, numbers 2, 3, and 4. 2 and 3 are really no different than one another when it comes to process. It's just you have a different interior angle sum for what there is. Let's count the number of sides there are. Sometimes angles is faster to do. But 1, 2, 3, 4, 5, 6. This is also a 6-sided shape. Make no bones about it. We already know the interior angle sum of a 6-sided shape. It's 720 degrees. So based off of that, we're going to add all of these angles. We're not going to divide by 6. This is an irregular polygon. Not all sides are the same. Or not all angles are the same either, which is the more important part. But if we add all these up, 130, 150, and that last angle, that is a 90-degree angle. And I wholly recommend that you write that 90. Otherwise, you very well might forget it. Not forgetting that something's 90 degrees. You just might forget to write it in general. So you have to remember to write it to then remember to write it. Anyway, I'm adding up to 720. It is a 6-sided polygon. Therefore, that will be its sum. Let's combine like terms here. And once again, it probably should be going off the calculator. X plus, let's see. It's 217, 347, 497, and 587, if I did that correctly. Remember, it's one of those things where if I did make a mistake, guys, double check your work against mine, add it up for yourself, use your own calculator. I set up the problem for you. The rest is algebraic. I'm only hoping I'm doing it right. 133, once again, might want to double check on that. I don't need the degree symbol because it shows x degrees there. So 133 for x. In some cases, I'll believe it based on the appearance of the scaling of the drawing. Now, once again, the only reason why I didn't do the d equals thing for this problem is because another problem already did it beforehand. That's right, we did this in the example problem. I'm not going to redo the exact same steps for something if I already have the number there on hand. In this case, I already knew the number, but that's neither here nor there. All right, so this one here, let's count. This time I'm going to count angles because just got to label it's easier. 1, 2, 3, 4, 5, 6, 7. So a 7-angled shape will have a different degree sum. And I don't know if it's obvious to you or not, but it's going to be 180 degrees more than a 6-sided shape. So a 6-sided shape was 720. Add another, it's not written here, 720. Add another 180 degrees, it's going to be 900. 180 times 5 is also 900. So 900 degrees is the interior angle sum of a heptagon. So let's add all of these up. We got x, 160, 2x, 125, 110, 112, and 147. And that equals 900. X plus 2x is 3x. So now we got 285, 395, 407. Wait, 507, shoot. 507 and 654. Oh boy. Let's just see if this ends up being divisible by 3. It looks like it will be. There's no reason why I don't think this will. 3x equals 246. That doesn't sound right. No, yeah, it does. 46, yeah. Divide by 3, x is 82. Does that look like an 82? Actually, I can't tell if it does. Let's just hope that that's correct. Once again, the algebra that's set up is left for you to maybe do the rest of the problem on your own if I made a mistake. Super apologies if so. I'm trying to see if this looks like an 82-degree angle. It looks less than 90, but it almost looks substantially less than 90. Maybe not. Maybe it's the angle at which I have to check it. All right, number 4. Sorry for not using the calculator here. It's even though it's right here on my phone. All right, these are exterior angle measures. I brought that up a bit ago. So I'm going to add these things up. 7x, 83, 33, 6x, and 49. And this will equal 360. Once again, it doesn't matter how many sides there are. Does not matter how many sides or angles there are. The exterior angle sum is always 360. And I talk about that more in section 7.1 if you want to look into it. 7x plus 6x is 13x. 83 plus 33, 116, 49, 165. And we get 195. Next equals 15. And they just ask us to solve for x, by the way. They don't ask you to find the value of the missing measures that have x in it or anything else. All right, guys, that is section 7.1, or at least the conversations to be had with it from what they gave us. Let's keep moving forward. Before we hit numbers 5 through 9, let's look at what section 7.2 has to offer. In section 7.2, properties of parallelograms, we start to learn some things about what a parallelogram is and what is true about parallelograms as a result. By definition, opposite sides are parallel in a parallelogram, but by virtue of that, opposite sides will also be congruent, opposite angles will be congruent, consecutive angles will be supplementary, and diagonals, like in number 7, diagonals will bisect each other, which means they're splitting them in half, basically, intersecting right at the middle of one another. So use the opposite sides theorem to find the value of x in the first example, finding x. AD and BC should be exact same length, so x plus 6 will equal 9. Subtract 6, you get x equals 3. The opposite angles theorem states that opposite angles are congruent, so y's measure is 66. Or y's answer is value 66 because B and D should be congruent to each other. So that's what's true in that parallelogram. Let's take a look at number 5 with a very similar thing that we could begin with if we wanted to, and I believe I will. 101 is opposite the B, so B will be 101. Opposite angles are congruent in a parallelogram. A is going to be something that is supplementary with the 101 or with the B. There are consecutive angles in a parallelogram, and just as a reminder, this is two parallel lines, for example, cut by a transversal that makes same side interior angles. Same side interior angles are supplementary. They add to 180. So A is 180 minus 101, which is 79. 79. That's all for number 5. Pretty straightforward problem. Number 6, this time let's find A first and we'll find B second. So on number 6, it is a parallelogram. Note that they do identify, it's not because it looks like it. They identify that in this part of the problem here, but there's no markings otherwise that would indicate it. So we go by that. Parallelogram, opposite sides are congruent. A minus 10 is going to equal 18. Those are the side lengths of those opposite sides there. We get to add 10 to both sides, and A is going to equal 28. Very, very straightforward sets of problems sometimes with these once you set up the thing. Opposite angles are congruent with that B. B plus 16 equals 103. If I wrote that correct, yep. Let's subtract 16 from both sides, and B is 87. There's number 6. Number 7 has to do with the diagonals of the parallelogram. Diagonals do bisect each other, so like I said, it splits them in halves, but it splits them into congruent parts. So this guy will be the same as this guy, and then this guy will be the same as this guy. The diagonals aren't necessarily congruent to each other, no, but the parts of the diagonals that are split will be congruent to each other. So let's begin with the C. C plus 5 equals 11, for example. Those two parts are going to be the same. Subtract 5 from both sides, and you get C equals 6. And D, I think this is D plus 4. D plus 4 equals 14. Subtract 4 from both sides, you'll get D equals 10. So that's what happens there with parallelograms. They have a few more problems down below, numbers 8 and 9, which look like they will be graph-based. So if you're ready for that, I am. Let's move forward into number 8. Find the coordinates of the intersection of the diagonals of parallelogram QRST with vertices here. So I'll go ahead and plot those. Now they ask for the intersection of the diagonals. I did mention a couple times here now that the diagonals bisect each other in a parallelogram. Well, if you have the points of a graph, the points of a parallelogram on a graph, what we can do to find where they intersect, besides just drawing two diagonals and say, oh yeah, that's where they intersect, which I'll kind of do, is find their midpoints. Because if diagonals bisect each other, that means they intersect at each other's midpoints. So if we find the midpoints of said diagonals, then we'll make that so. And I'm sure if we did just draw the lines, we'll go, oh yeah, look, that's where they intersect. But if they're at some half points, you might want to think a little more closely on how you're going about that. So what if I did this here, just kind of a faint dotted line diagonal here and here. It looks like we have the diagonals bisecting each other right there at -2, -1. And I'm sure that's the correct answer. Let's say we didn't have the graph. Let's say that we wanted to know a few more things about this and what's going on. What we want to look at more so now, let's label these. Q, not just label, but actually give the ordered pairs. Q is -8, 1. R is 2, 1. S is 4, -3. And T is -6, -3. By the way, I should only have to find one of the midpoints, knowing that they are concurrent. Both midpoints are concurrent. The lines are concurrent at the respective midpoints, I should say. It only takes one to actually find. So let's find the midpoint from T to R here. The midpoint from T to R by tracing how far over and up I need to go, and we'll go half those distances. I recognize there's a midpoint formula, which I will also include, because I suppose if you're on the review portion, your teachers might require that, and you might not have the graph. But let's count from -6 over to 2. That's over 8. And from -3 to 1, that's up 4. Well, let's go half those distances. Instead of going over 8, let's go over 4. Instead of going up 4, let's go up 2. And boom, you still land yourself on that point. And that's one way of discovering what that midpoint is. Once again, the midpoint's at -2, -1. So that midpoint, -2, -1. If you want to see another example of that, let's do the midpoint by calculating the average of those two values for T and R. The midpoint of segment TR is going to be at averaging your x's, -6 plus 2 divided by 2, comma, -3 plus 1, all divided by 2. So this is going to be -6 plus 2 is -4, and -3 plus 1 is -2. And -4 divided by 2 is -2. And -2 divided by 2 is -1. -2, -1. So that's probably the better mathematical way that they'd be expecting you to do something like that. And that's where we get the midpoint. But once again, if I'm using graphs, that's how I'm going to go about it. A lot of counts, and you're going to see me do that probably more than that. And by the way, QS's midpoint is going to be the same one. That's my point. The diagonals bisect each other in a parallelogram. And by extension, that means they bisect each other in rhombuses, rectangles, and squares, things that we'll talk about later. Not so in trapezoids or kites. Okay. Number 9. 3 vertices of JKLM are J, K, and L at those respective points. Find the coordinates of vertex M. This one I think a graph's a little more expected, and I'm strictly going to go based off the graph slopes count. No other way I'm going to talk about it. So J is at 1, 4. K is at 5, 3. L is at 6, -3. I need to find M. J, K, L. Now, it is important that they do call it parallelogram J, K, L, M, not just because it's alphabetical or whatever. If you didn't know the alphabet, that's fine. But the letter order in which that they did mention is imperative to how you go about connecting the segments in this drawing and trying to find M, because there are 3 different ways that a parallelogram could be drawn, and I'm sure you can imagine that this is the one we're trying to find here. But it's very possible that it could have been up here for a parallelogram, right? Boom. Or it's very possible that it could have been, let's see, I gotta imagine this. Boom, boom, boom. Or it could have been somewhere over here, right? Boom, 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 boom for a parallelogram. But because it's J, K, L, M, they need to connect in such a way as well. So we do know that J, K, and L actually do connect together like this. And M needs to connect to both J and L. So whereas M, we can track it a couple different ways. Let's work off slopes from, say, K to J. We go left 4 and right and up 1, left 4 and up 1. From L to M needs to be the exact same because parallelograms need not only parallel lines but opposite sides congruent, so the same over and up amounts. So that's one way we could go about it. We also could have gone down from K to L, gone down 6, right 1, and then from J to M, down 6, right 1. M should be right there. M is at the point 2, -2. That's how it works. Just work off slopes, how much you count in certain directions to work off parallel lines and equal distances. And that is properties of parallelogram 7.2. Now 7.3 is not to be outdone with the fact that we still do talk about parallelograms, but in their own right, proving that are properties of parallelogram. So, a quadrilateral is a parallelogram. So there are some theorems known as converse theorems saying we have a quadrilateral that has, opposite sides congruent. And that makes it a parallelogram. It must be a parallelogram. Diagonals bisect each other. There must be a parallelogram. There's a new one as well to show that something's a parallelogram if we have a quadrilateral with one pair of opposite sides congruent and parallel. And that's what they're showing actually right here. But the opposite sides parallel and congruent theorem, if one pair of opposite sides are congruent or are in parallel, then it's a parallelogram. You're given that the sides are parallel, what value of x would make these equal, making it a parallelogram, basically. That's what they're saying. For what value is it a parallelogram? No change in what you do. Set these equal to each other to make it so. X would equal 6 if you do the algebra. Now they also ask you to find the lengths of these guys right there, and you substitute 6 and 4. No, excuse me, I don't think they ask you to find the lengths. That gets you to confirm that you get the same length out of 19 for each of those. Okay, so number 10, state which theorem you can use to show the quadrilateral is a parallelogram. Note that there's nothing to actually solve for here. They're just saying that this should be enough information to tell us what theorem it is. And I don't remember all of them by name. I'm going to try my best that I can. This is the parallelogram opposite sides converse, I believe it's called. So number 10. Parallelogram. I believe these are ones that opposite sides converse. It might be the opposite sides congruent theorem. This is where I wish that I looked it up. Excuse me, converse. Not only do I wish I looked it up, I wish they showed it here. This is all about review, and they're saying, hey guys, we're going to review the stuff. By the way, here's the answer. But I guess that'd be too direct. They're saying, here's the answer. Now I'm going to ask you a question. What's the answer? You have it on the same page. All right, number 11. This is showing diagonals bisect each other. I can tell by the congruent tick marks here, and then the 6's being the same there. If the diagonals bisect each other in a quadrilateral, it is indeed a parallelogram. This is the, if I know the name correctly, and I'm not guaranteeing this at all, parallelogram diagonals converse. Now these are converses. Remember, a converse of a theorem switches the if and the then. If a quadrilateral is a parallelogram, then the diagonals bisect each other. If a quadrilateral's diagonals bisect each other, then it's a parallelogram. I just don't know if that's the name. Now, not all theorems have true converses. These ones do. These ones do. And then for this one, it's the opposite angles theorem. So parallelogram, opposite angles theorem. Once again, for the stuff you have, markings in the 57s and stuff like that. Angles converse, I should say. So, sorry if it's not the exact same one. I'm not really looking it up at the moment while we're doing it, but I think that's decent with respect to what it's actually stating. All right, number 13. Find the values of x and y that make the quadrilateral a parallelogram. So, it's no different from what we did in section 7.2 when you knew you had a parallelogram. You set opposite sides equal to each other. Because we're saying if we use the parallelogram opposite sides converse, 4x plus 7 equals 12x minus 1, what value of x would make these things equal? And if opposite sides are congruent, then you have a parallelogram for both pairs of sides. So we set them equal and we solve. Subtract 4x, add 1, divide by 8. There's your x. For y, same thing. We got y plus 1 equals 3y minus 11. So no real trickery in what you're doing. It's just why we're allowed to do it. It's a completely different story. And I'll say this. In a vacuum, we know we're in section 7.3 doing this review. On a quiz, you'd have to be well aware that this is talking about a parallelogram. In a rhombus, it might be a different kind of question than this. And in a square, you know what I mean? So it just depends on what you're actually doing with them. But those would be the answers for those. I'll trust my own algebra that those are correct. All right, well, we'll make this a parallelogram on number 14 using the diagonals converse, that they'd have to bisect each other. These two parts would have to be the same on number 14, where 6x minus 8 will have to equal 4x. Let's subtract 4x from both sides and add 8 to both sides and divide both sides by 2. We'll be getting x equals 4. To double check that, 4 times 4 is 16, 6 times 4 is 24, minus 8 is 16. They'd both be the same. It would make it a parallelogram. I wish there were trick questions here and there that says, or is that enough information? In which case it is, but maybe if they had a few. And then going back to a graph, show that quadrilateral WXYZ with vertices here is a parallelogram. So now what we have to do is go off one of those those theorems, those converses, if you will, and work this thing out. And I will strictly go off the graph stuff, no distance formula, but Pythagorean theorem, no slope formula, but counting rises and runs. So W X 28 Y and Z. Okay. We can't say it looks like it, because I could make a parallelogram I can make something else that looks like it and is not. We're going more based off other information. So we got so many options here, guys. Remember, any of these things hold true. I wouldn't go off the angles one. Because it's really tough to talk about angle measures in graphs. Sure, they look congruent, but that's not really something we're going off of. Instead, you got some options here. My preferred one really is the one they brought up here. And since we haven't talked about it yet, let's. Opposites, one pair of opposite sides parallel and congruent. So what I could do here is if I went from Z to Y and did how much run and rise here, over 3 up 2, and this is over 3 up 2, that really is enough information for me. Now, I'm going to write out what that information's telling me. What it's telling me is that the slope of WX, segment WX, is up 2 over 3. Don't mistake it for 3 over 2. It's 2 over 3. And the slope of YZ, segment YZ, is also 2/3. Now, one pair of opposite sides parallel is not enough for a parallelogram. In fact, that's the definition of a trapezoid, unless you show that the others are parallel, which we could do. But it's also about these distances. What is the length of XW? Segment XW. XW squared, this is a Pythagorean theorem. A squared plus B squared is C squared. So we can do like a 3 squared plus 2 squared here. So 9 plus 4, which is 13. So XW is the square root of 13. And I mean, I believe that it should make enough sense logically that this is the same right triangle exactly. That's why I said it's enough information. That's also the square root of 13. YZ is the square root of 13. So XW, I probably should have said WX. XW and YZ are the same length as well. That checks out, just as the slopes are the same. Slopes of these, right, like that. By the opposite sides parallel and congruent theorem, this is a parallelogram. By the opposite sides parallel and congruent theorem, WXYZ is a parallelogram. Let's shrink that. Okay. They're not trying to trick you, and is it or is it not? It absolutely is by that. Okay. Now, I didn't check to see whether these sides were parallel or congruent or anything like that. I didn't check whether the diagonals bisect each other, and all of those could have been absolutely valid. This was one method I went by. The very moment I went up 2 over 3, for both those sets of opposite sides, it was guaranteed to be a parallelogram. But showing more, I think, is probably more beneficial for this. All right, that's section 7.3. We got 2 more sections to go. We're about a half hour into this thing. Let's take a look at section 7.4. Looks like this is part of the review portion, and on the next page will be the 7.4 questions. This is where we hit rectangles, rhombuses, and squares. We still have a few problems to go. What are we going to? Number 28. So 7.4 and 7.5 seem to hit a good smattering of 13 more questions. Wow, okay. I didn't expect that. All right. Classify the special quadrilateral. Explain your reasoning. So only 4 right angles here. Notice they said quadrilateral, not parallelogram. But a quadrilateral with 4 right angles is going to be a rectangle. By the rectangle corollary, it's that because they're not marked as congruent, you cannot conclude it's a square. Doesn't mean it can't be a square. Just means we don't know for sure. So the most specific we can guarantee ourselves is a rectangle. And that's the only instructions that they give us. Yeah, they're going to give us a lot more for 7.5 afterward on trapezoids and kites. But here we got 16 through 20. We're going to talk about rhombuses as well. There's a corollary for that. If all sides are congruent, it's a rhombus. If all sides are congruent and all angles are right angles, it's a square. You know, it's a rectangle and rhombus put together, which are all parallelograms, by the way. So they inherit everything that's true about a parallelogram, and they add some things on top of it. I'm sure I'll talk about them if they bring them up. Classify the special quadrilateral. Explain your reasoning on number 16. The 56 degrees isn't really saying much to me, except saying that it's not a square, because it's not a 90-degree angle, but all 4 sides are congruent. This is a rhombus, because all 4 sides are congruent. And one angle is known to not be a right angle. This is a rhombus. Now, I want to bring that thing up again. Knowing it's a rhombus means it's also a parallelogram. Rhombuses are parallelograms, every single one of them. They didn't show opposite sides parallel. Technically, they're showing opposite sides congruent, though, but since all sides are congruent, it's a more specific type of parallelogram. The reason I bring that up is because I could also determine what all these angle measures are. Opposite angles will be congruent, 56 and 56, and consecutive angles would be supplementary, where this is now, 124 and 124. So it's definitely a rhombus, and definitely not a square with that in mind, because I can determine all the angle measures there. It's also definitely a parallelogram, but more specifically, it's a rhombus. Number 17, we only have opposite sides parallel. Nothing more known, so no guarantee that it can be more than that with that in mind. Both pairs of opposite sides, I might have to sneeze here, parallel, but nothing else is known. So this is definitely a parallelogram. Definitely a parallelogram. But with no certainty, is this a rectangle, rhombus, or square? Which it could be. It could be. There's nothing else that's known. You can't say it's not a square just because how it looks. If they told you all of them were right angles and stuff, great. They don't tell you that. We don't know that for sure. Definitely a parallelogram. Number 18, 4, 4, 4, 4. Because all sides are congruent, this is at least a rhombus. Now, I want to let you know that without knowing that information, I mean, this is important anyway, but without knowing that information, 2 right angles alone couldn't guarantee that this would be a rectangle. Since all rhombuses are rectangles, parallelograms, consecutive angles are supplementary, and right angles are how should I say this? Since all rhombuses are parallelograms, opposite sides are parallel, and a side. So here's what I'm trying to say. These right angles, with this being a parallelogram, is enough to tell me more stuff. These are parallel, and a line perpendicular to a line parallel to another line. Let's see. How do you say that again? When 2 parallel lines are perpendicular to the same line, when a line's perpendicular to a line, oh my gosh, how do you say this? When two sides are parallel, when opposite sides are parallel. Oh, we already have that. And when one of them is perpendicular to a line or to a side, so will be the other one. Basically, what I'm trying to say is this. And I'm not done, by the way. I'm not done writing. What I'm trying to say is this. I know with certainty that this is also 90 degrees. And I'm probably overstating what I need to state here. But this is absolutely 90 degrees. And this is also absolutely 90 degrees. They have to be. Because of the nature of parallelograms. Without those 4s there, I wouldn't have known this was a parallelogram. Remember, it's a rhombus, but a rhombus is a parallelogram. But without those 4s, I wouldn't have known that. You see, I could have made, for example, a kite is a classic example. I can make a kite like this. Quadrilateral with 2 right angles here and here. They're opposite angles, and they are right angles. That doesn't make it a rectangle or a square or anything like that. I don't know that guarantee, but knowing this is a rhombus allows me to get into that mindset. And once again, I'm over-speaking on this problem. I understand that I am. But this gets you to know those are right angles. Therefore, all angles are right angles. And this is also a rectangle, which means this is a square. So that's the big ending I need to go with here. It's a rhombus, and because it's a rhombus, I have enough to say it's a rectangle, and because it's also a rectangle, sorry, with the right angles, I have enough to say it's a rectangle, and therefore it's a square. A little tricky. Maybe you start to try and make that assumption, but we can't make the assumption. Understand why we can hit home with that. Knowing it's a parallelogram is, I think, super important there. Number 19, find the lengths of the diagonals of the rectangle WXYZ, where WY is negative 2x plus 34, and XZ is 3x minus 26. Okay, let's kind of draw that, especially since it's not drawn, and the letter order is, once again, super important for this. So I'm making something that's rectangular in nature, WXYZ is how they called it. You have to circumnavigate your object that way. And notice how they did the letters for these lengths here. They didn't say like WX and YZ. They said WY and XZ, these diagonals. In a parallelogram, which a rectangle is, in a parallelogram, diagonals aren't necessarily congruent. But in a rectangle, diagonals are congruent to each other. WY is negative 2x plus 34. XZ is 3x minus 26. In a rectangle, these equal each other. WY equals XZ. So we set negative 2x plus 34 equal to 3x minus 26. And let's solve for x. They said find the lengths of the diagonals. Let's solve for x, and then let's use that to find the lengths of the diagonals. I'll do some blue or something. Getting a little black colorblind here. Add 2x to both sides, add 26 to both sides, divide both sides by 5, you get x equals 12. Now to find the lengths of these things here, remember they're going to be the same length, so I just need to substitute it into one of them. WY and XZ being the same length. Let's do the 3x minus 26. 3 times 12 minus 26. 36 minus 26, which is 10. This is the final answer that we're getting right there. Let's kind of point to that so we know for sure. And negative 2 times 12 is negative 24 plus 34 is also 10, so that works out. All right, and then lastly for the section, number 20, decide whether parallelogram JKLM with vertices here is a rectangle, a rhombus, or a square. Give all names that apply and explain. Generally, they don't say give all names that apply, but here's the thing. If it is a square, that means it's also a rectangle and a rhombus. I think it is crucial that they tell us it's a parallelogram first. That means we don't need to test things such as opposite sides are parallel, and that means we have to do very minimalist testing here. And I'm going to show you which minimalist testing I'm going to decide to do. It's based on the kind of shape that they give us. I'll show you what I mean, especially if it holds true for this thing. So 9,6 for K, and then L is 7,2. Never mind. I was going to do maybe a diagonals test, but I won't here because they are diagonal and they're not. I don't know. They're not vertical and horizontal like you might have seen in some of the earlier problems out of the sections. Now it's looking very square-esque, which is probably good for the review's sake, because then I could answer exactly what I said before. If it's a square, then it's also a rhombus and rectangle. But let's really just test for rhombus and rectangle here. Now, the way that I want to test it is like this. I already know it's a parallelogram. They actually say that. They say parallelogram JKLM. I'll even write it here. Parallelogram JKLM. That's important because I already now know opposite sides are parallel, opposite sides are congruent. I know diagonals bisect each other, things like that. All I need to figure out, though, is that a parallelogram with consecutive sides that are congruent like that would make it a rhombus. Because these will already be congruent to each other. Boom, that would make it a rhombus. A parallelogram with a right angle would be a rectangle, because then opposite angles would be congruent, consecutive angles would be supplementary, things like that. It would be a rectangle. I just need to really do one set of tests here. And honestly, this is it. This is it. Let's test the slope from M to J and the slope from M to L. This will tell me two different things. Not just the slope, but the rise and run, the count. Because if I have to reduce the fraction, I get it. Like this is up 1, 2, 3, 4, and right 2. This is down 2, and right 1, 2, 3, 4. This tells me everything I need to know about this. Let's go to work on what it's actually telling me. The slope of segment MJ is 4 over 2, which is 2. I'm going to put 2 over 1 to satisfy a little something else. And the slope from M to L, which is down 2 over 4, is negative 1/2. These are opposite reciprocal slopes of each other. Opposite reciprocal slopes means the lines are perpendicular to each other, which means this is a right angle. Because you have opposite reciprocal slopes, this is guaranteed to be a rectangle. Now the other part of this, and I mentioned this in a previous bit with showing something's a parallelogram, these are the same right triangle distances, legs of 2 and 4. It doesn't matter if 2 is negative or positive, it's a 2. 2 squared plus 4 squared is this, 2 squared plus 4 squared is that. Whatever that length is, square root of 20, 2 root 5, 2 root 5 and 2 root 5, they are the same length, absolutely. So JM's length is the same as ML's length, which means those are congruent to each other, which means all sides are congruent, right? It also means these are all right angles here. But all sides are congruent as well, which means this is a rhombus. Now, a rectangle rhombus is also known as a square. A square, all congruent sides, all right angles. So these are the three known shapes that we're going to call it. The big daddy, the most specific classification we can call it is a square. And it looks like a square. But I only needed to do one test for that. Now, an alternative test I could have used was the diagonals. If the diagonals of a parallelogram, let's go more specifically. If the diagonals of a parallelogram are congruent, then it's a rectangle. If the diagonals of a parallelogram are perpendicular to each other, then it's a rhombus. So we would have, and that would have been true. I didn't test that. And I would have tested it if it was more vertical and horizontal. That would have been a very easy test to do. And I'm glad the problem was presented the way that it was. All right, let's move forward. Before we actually hit number 21, let's look at the last section of what's going on, properties of trapezoids and kites. Of course, I did these sections as well. I just did 7.5 as a recent video, so you can find that one before this one in the IM2 playlist. So let's take a look at what they want to talk about on trapezoids and kites. They use a graph-based version of examples, find the mid-segment, length of mid-segment of a trapezoid. It's really weird when they do these example things. They're like, this covers the entire section. Not even close. They don't even bring up kites here or anything about trapezoid base angles and diagonals being congruent and for isosceles trapezoids. Find the length of mid-segment EF here. So they find the lengths of segments AD and BC, the bases of a trapezoid, the ones that are actually parallel to each other, and then they average those two values. They add them up and divide by 2 or take half of it, and that gets you the length of the mid-segment. It is the average of your two trapezoid base lengths right there. So if we're going to be asked to do the same thing, I'll make sure to follow up. What we could have also done was found the midpoints of each of these here and found this individual length. You know, Pythagorean theorem, a squared plus b squared, that kind of stuff. We'd also get 4 root 2. That's an option, but that's only unique to the graph-based version of it and not to non-graph-based versions of it. All right, problem number 21. Find the measure of each angle in the isosceles trapezoid WXYZ. the angles, because they didn't talk to us about base angles and such, I guess I have to talk to you about it, and trapezoid, isosceles trapezoids. They tell you it's an isosceles trapezoid by, not just by appearance, but by what they mark as congruent here. These are known as the legs of the trapezoid, and here are the bases. That means we can know that these are the ones that are parallel to each other. These are the ones that are congruent to each other. It's important to note the difference because base angles, ones that are made from the same base, are going to be congruent to each other. Z is also going to be 58 degrees because it's going to be the same as the measure of angle Y. They are congruent in an isosceles trapezoid, mind you. Not any old trapezoid, but an isosceles one. Now, W and X, same thing as parallelograms. They are consecutive non-base angles here, but they will be supplementary to each other. Measure of angle W is going to be the same as measure of angle X, and those are found by doing 180 minus 58. They're supplementary in that way. So this is going to be 122 degrees for each of those. 122 and 122. There's your isosceles trapezoid angle measures. Number 22. Find the length of the midsegment of trapezoid ABCD. Not isosceles trapezoid, and I don't think that's really going to matter much. So this MN, if you will, I'm going to call it MN because they didn't actually here. They tend to actually call it MN in some of the other ones, but I'm going to do it here. So number 22, we got to average the lengths of AB and CD, just like you saw in the graph one before. We're going to average 39 and 13, add them and divide them by 2, or take half of them. That's half of 52, which is 26. Not degrees, this is a length. That is the length of the midsegment of trapezoid ABCD from what we see mentioned there, given that that is the midsegment. Number 23. Find the length of the midsegment of trapezoid JKLM with these vertices. So this will be like the example that you saw. Let's put that into play and start that graphing process. J, K, 10, 6, L, 8, 2, M, 2, 2. M, J, K, L. Is this a trapezoid? I must have 9-2 marked, not 8-2. I was going to say, that doesn't look like a trapezoid. There we go. All right, much better. Okay, so being a trapezoid, I'm imagining these are the parallel guys right there. Again, it looks a little better than it did previously. So if these are the parallel ones, the midsegment's going across this way. And I think I'm clearly actually truly seeing the midpoints for what they are. Remember, midsegment's made by midpoints. So it would actually be these sets here. If you wanted to, one option is find those midpoints and then count your distances by, once again, I'm a Pythagorean theorem guy, that rise and run, how much, up and over, things like that. Over 3, up 1, 2, 3, 4, 5, 6. So if I call it, how about AB this time, just because they use M already. The length of AB is 6 squared plus 3 squared. So AB is the square root of 45, which is 3 root 5 if you simplify the radical. That's one option. The way that they kind of do it more so is they work off of the lengths of JM and KL. So you could also find these lengths and average them. Might take longer, but it depends on how long it takes you to find midpoints. So from J to M, or M to J, that's up 8 and over 4. So JM is 8 squared plus 4 squared, or JM squared. So JM is the square root of 80, which is 4 root 5. So there's JM's length. KL is over 2 and up 1, 2, 3, 4. We saw that before as root 20, which was 2 root 5. I'm just going to call that out because we did that for a previous problem. 2 root 5. So AB, in that case, will be half of, let's do that again, will be half of 4 root 5 plus 2 root 5. which is half of 6 root 5, which is 3 root 5. So you still get 3 root 5 no matter which way you do. The bottom method probably takes longer, but it makes more sense to know because you are doing mid-segments. That's how you would do it when it's not on a graph. We're not doing midpoints on things that aren't on graphs in some other situations, so I think that probably makes more sense. All right, number 24. This says a kite. Let's see what they want us to know about a kite, and maybe I'll make more mention about what a kite has when we're ready. Number 24, a kite has measures of 7x degrees, 65, 85, and 105. Find the value of x. What are the measures of the angles? What are the measures of the angles that are congruent? So listen, a kite's just another form of a quadrilateral. Without making the drawing, first, we can answer this regardless because any quadrilateral's interior angle sum is 360 degrees, period. Doesn't matter if it's kite, parallelogram, square, rhombus, rectangle, or trapezoid. They add to 360. So we'll solve from x for there, for x from there. 7x plus, that's 150 and 255. 7x is 105, so x is 15. Okay, so there's x. Now let's do 7 times 15. 7 times 15 is 105. I was taking some time with that. 105 degrees. So the congruent angle measures. What are the measures of the angles that are congruent? 105 degrees are the congruent ones. So let's kind of say what that looks like on a kite. So a kite, and I have to kind of make up one. I'm going to do it this way. Give me 1 second. This is kind of a makeshift version of how I'm going to do my own kite. Let's delete this. Okay, a kite is a... Like I said, I'm makeshifting my own. Hold on. A kite is a quadrilateral with 2 sets of congruent... Uh-oh, something happened here. No! I have to restart something because it's not showing my marker. I knew something happened when that happened. See, it's not showing my pen tool here, so I'm going to save this. Let me pause my thing, and I'll bring it back up. Okay, I'm back in business. Now my pen shape is back. Okay, so a kite is a quadrilateral with 2 sets of consecutive sides congruent, such as these ones, and opposite sides are not congruent, so nothing's parallel. Nothing's parallel. Now, with this in mind, some things are going to be true. One of them is that one pair of opposite angles are also congruent. It would be these ones. This would be the example of the two that would be, for example, 105 degrees, like that. If those are 105, I mean, this isn't clearly drawn to scale then. If this is 105, maybe then this is the 85 and this is the 65, you know, like that. So they still add to 360 in that way, but these are the ones that would be congruent. These are the ones that wouldn't be congruent. There are also things that are true about its diagonals. We'll see if they need to bring it up, but that's the end to number 24 as far as answer goes. All right, number 25. Let's see if they talk about kites again. Quadrilateral, nope. Quadrilateral WXYZ is a trapezoid with 1 pair of congruent base angles. Is it an isosceles trapezoid? Explain your reasoning. Trapezoid with 1 pair of congruent base angles is a trapezoid. Explain your reasoning. Yeah. Yes. So they say base angles specifically. So yes, because the other two, I mean, listen, there's a theorem that I believe brings this up, or a converse theorem or something like that, because the other two base angles would be supplementary to the congruent base angles, and therefore would also be congruent to each other. This is also a theorem. Yeah, it would make an isosceles trapezoid. So basically all they're saying is, I know I have a trapezoid, so like boom. I know I have a trapezoid, and in this trapezoid, and in this trapezoid I know that these angles here are congruent. Would it make an isosceles trapezoid? Yes. It would make these two angles congruent, right? These supplementary to those and supplementary to those. Like, if these were both 100, then these are both 80. And both 80 is both congruent. It's only going to be true of isosceles trapezoids there. It would make everything else true within there that an isosceles trapezoid would have. All right, number 26. Give the most specific name, or 26 to 28. Last three, give the most specific name for the quadrilateral. Explain your reasoning. We should be able to get this done before the hour mark is finished. Number 26, you only have one. In fact, I think I'll type all of this. You only have one pair of parallel sides known. That is a trapezoid. 26. Only one pair of sides is parallel. So this is a trapezoid. Now, it could be, we don't know if others are parallel. If the other pair of sides were parallel, then it would be a parallelogram. But we don't know that. And the reason I make this distinction isn't so much to answer the question of the problem, it's to help review with you guys, right? This is all about review. Trapezoids are not parallelograms. If you have two pairs of parallel sides, it's no longer a trapezoid. It is only a parallelogram. Kites are not trapezoids or parallelograms. Kites cannot have any parallel sides, so that's just important to know. All right, number 27. Quadrilateral with all sides congruent. It's a rhombus. Rhombus, quadrilateral with all sides congruent. That's just what we know about a rhombus, right? That's how we dive into that muck. It could be a square if we knew there was a right angle somewhere. A rhombus is also a parallelogram, definitely not a kite or trapezoid. Number 28, last one, we have a rectangle. And it's probably not a square, keeping in mind the sets of congruent side marks that we have. All right angles and consecutive sides are shown to not be congruent. So it is not a square. Right? Whenever I have two tick marks for one, I'm not just saying that, oh, they're congruent to the sides opposite. It's generally also a way of saying that they're also distinctly different from these ones that are right here, for example, right? So that would just be a rectangle, not a square, with that in mind. Guys, that's the last problem on this thing. So, hey, that ought to do it for this. I'm hitting the save button here. So that ought to do it for this one. We did it within the hour. Awesome. Almost a power hour, if you will. This is Mr. Robinson. Thank you so much for watching this for the Chapter 7 review. Did it hit every kind of question under the book, under the sun, and in the books? No. It hit a lot of them, though. A good section of them. I'm trying to think of ones, they didn't talk about rhombuses diagonals being perpendicular to each other, trapezoids diagonals being congruent when they're isosceles, a kite's diagonals being perpendicular to each other as well, and one bisecting the other. That stuff wasn't brought up, and, those kinds of questions could always be asked. But there's going to be the Chapter 7 test as well that I'm going to be doing a review on, and of course the cumulative assessment to look at some of the other questions. If you want to see more on this, guys, check the description section down below, check the playlist, check the timestamps, check the PDFs that I have for you, and hopefully all was very helpful. So thank you guys. That ought to do it for this one. Take care, and I will see you in the next one.